Assalamu alaikum wa rahmatullahi wa barakatuh. Hello everyone. Welcome to lecture 27, Organic Chemistry 1. Today we will continue on chapter 7, Alkyl halides, nucleophilic substitution, and elimination reactions. Stereochemistry of the E2 reaction. E2 elimination requires partial formation of a new pi bond with its parallel p orbitals in the transition state. When the hydrogen and halogens are anti to each other, the dihedral angle theta equal 180, their orbitals are aligned. This is called anti-parallel conformation. When the hydrogen and the halogen eclipsed, dihedral angle theta equal to 0, their orbitals are once again aligned. This is called syncopalar conformation. Of these possible conformations, the anti-coplanar arrangement is the most commonly seen in E2 reaction. As you can see, when theta is 180, hydrogen and halogen are anti-coplanar. The base will attack on the hydrogen. The two electrons will go and form a pi bond while X is going out, and the transition state will be clearly abstracting of hydrogen, formation of pi bond, loss of leaving group. This is transition state. When theta dihedral angle equal to 0 and the CH-CX in the eclipsed conformation, we call this syncoplanar transition state, and the base will attack on the hydrogen from the same side where you have here high electron density of the lone pairs and sigma X carbon halogen sigma bond. So there is a repulsion, and this transition state will be higher in energy. Okay, as an example of seeing the syn elimination, starting with 2-bromo bicyclo 2,2,1 heptane 3 deuterium. This is deuterium. Okay, building a model 3D, we will see that the H and the carbon hydrogen and the carbon halogen in this form, they are syncoplanar, while the carbon bromine and carbon deuterium are not anti-coplanar. So the base will attack on the hydrogen forming double bond, and the Br is out. And we can get clearly the deuterium in the product, bicyclo 2,2,1 hept 2 in 2D. Here we said the number 1, 2, as the bromine comes first. Okay? So 1, 2, 3, 4 versus 1, 2, 3, 4. Why? Because numbering from this side, the Br will be number 2. The other way around, the deuterium will be number 2. Which one? Because they are the same, here 2 and here 2. Okay, which comes first? Alphabet Br. So here is 2 bromo and 3 deuterium. In the product, this will be number 2 because there is no other substituent. So that will be 2 deuterium. So number system will be 1, 2, 3, 4, 5, 6, and 7. That's why we call it HEPT. We have taken that before in the previous lectures. The E2 is a stereospecific reaction because different stereoisomers of the starting material react to give different stereoisomers of the product. This stereospecificity results from the anti-coplanar transition state that is usually involved in the E2 reaction. Compound 1s2r, 1-bromo 1,2-diphenylpropane, when reacted with sodium methoxide, we get trans 1,2-diphenylpropene. Taking the compound, the structure, to 3D structure. Okay, we have bromine, hydrogen, and phenyl. We have bromine, hydrogen, and phenyl. And front carbon, this one will be hydrogen in here, CH3 in here, phenyl on this side. Now we have to rotate this on this way to get the hydrogen down. So the phenyl will be on the right, the methyl will be on the left. Now the hydrogen, carbon hydrogen, and the carbon Br are anti-coplanar. Base will attack on the hydrogen, abstracting the hydrogen. These 2 electrons will go to carbon-carbon bond, forming double bond, and Br is out. As you can see here, this phenyl on the right, this phenyl on the left, so they are on opposite side. That's why we get the trans form. The other isomer, where we start with 1s, 2s, 1-bromo 1,2-phenylpropane, drawing the 3D again, phenyl, Br up, Br, H in here, okay. Here is phenyl, hydrogen, CH3 on the other side, okay, and hydrogen in here. So that is anti-coplanar. Base will attack, forming double bond, losing Br. This is the transition state. Methoxide approaching, bromine is leaving, and the formation of alkene. So we have here CH3, phenyl, hydrogen, and the B orbit of the pi bond in front, and there is another one in the back, forming double bond. Because the 2 phenyls are on the same side, we get here the cis 1,2-diphenylpropane. To summarize the differences between E1 and E2, Base used in the reaction, weak base. In E2, we need a strong base. Solvent for E1, good ionizing solvent, while in E2, wide variety of solvents. Substrate that are active in E1 mechanism, tertiary alkyl halide and secondary alkyl halide. On the other hand, E2, tertiary, secondary, primary. And in both cases, leaving groups should be good leaving groups. Characteristic for the E1, in E1 first order depend only on the concentration of the substrate, alkyl halide. E2 second order depends on both alkyl halide and the base. Orientation, most substituted alkene should be the product, most substituted alkene will be the product, because we said according to Zaitsev rule, the more substituted alkenes are the more stable. In stereochemistry, no special geometry in the E2 mechanism, coplanar transition state required. Rearrangements are common in E1 mechanism, but they are impossible in E2 mechanism. Predicting reactions mechanism. SN1, SN2, E1 or E2. The first, we look at the substrate. Alkyl halide, is it tertiary? If it is tertiary, is the leaving group good? And does the solvent have high dielectric constant? If no, there is no reaction. If yes, is the nucleophile basic? If it's no, then it's SN1 mechanism. Does the substrate have a hydrogen on the adjacent carbon? If no, it's confirming that it's SN1 mechanism. If yes, there is a possibility of another mechanism. Is the base concentration high? No, it is E1. Yes, it is E2. Now, if the substrate is secondary alkyl halide, is the nucleophile good? Yes, we have to ask, is the substrate sterically hindered? If no, it's SN2 mechanism, concerted mechanism. If it's yes, does the substrate have a hydrogen on the adjacent carbon? At this point, if the nucleophile good and it's highly basic, if it's yes, we ask the same question. Now, if we have the substrate indeed has the adjacent hydrogen, then you ask high dielectric constant. If no, that's E2 mechanism. If it's yes, and the base concentration is high, yes, it is E2. No, it's combination of E1 and E2. Now, is the nucleophile from the beginning is high? If no, high dielectric solvent. If no, slow SN2. Yes, then you have SN1 mechanism, SN higher than SN2, and you also have an E1 mechanism. That's in case of secondary substrate. Primary substrate, primary alkyl halide, is the nucleophile good? If it's yes, SN2. If the nucleophile is not good, but its base is the nucleophile highly basic? If it's yes, does the substrate have hydrogen on the adjacent carbon? If it's yes, it's E2 mechanism. If no, it's SN2 mechanism. If the nucleophile is not that basic, but it has alpha hydrogen, if there is no alpha hydrogen, then it's slow SN2. If it's yes, no reaction or slow E2 SN E2 and SN2 mechanism. Now what we have to do is take an example of each of them. Tertiary butyl bromide in presence of sodium methoxide. Then, is the leaving group is good? Yes. Is the nucleophile basic? Yes. This is basic. Okay. Does the substrate have hydrogen on the adjacent carbon? Yes. Is the base concentration is high? Yes. It's E2 mechanism. You get to this. That's tertiary alkyl halide. But again, here the nucleophile is not that strong. It's not that strong. Okay. Now, is the leaving group is good? Yes. Is the nucleophile basic? No. So it is SN1, and as we know that SN1 usually accompanied with E1. Okay? Here an example of secondary alkyl halide. Is the nucleophile good? Yes, sodium isoxide in the first example. Yes, it's good. Okay. Is the substrate strictly hindered? No, not really. Okay, no. So we have SN2. Yes, we have this one. Okay. Now, does the substrate have hydrogen on the adjacent carbon? Yeah, we have hydrogen in here. We have hydrogen in here. Dielectric, high dielectric solvent. Yeah, methanol is high electric solvent. Yes. Is the base concentration is high, sodium methoxide? It depends on the concentration. If the concentration is high, so it's E2. So we have E2 as well as SN2 in the first example. Now, if we have the secondary, but you have methanol as a solvent, as a nucleophile, and heat, solvolysis reaction. Is the nucleophile is good? No. Is the nucleophile high basic? No. The solvent has high dielectric solvent? Yes. So we have as SN1. As we mentioned before, SN1 usually accompanied with E1. Primary. Here is primary. Is the nucleophile good? Yes. The first example, okay? Sodium methoxide. So we have SN2. And as we mentioned, SN2 usually accompanied with E as a minor product. Okay, now, primary alkyl halide, but using silver nitrate as a promoter for carbocation, methanol, and heat. We have mentioned before that silver salt and high temperature are used to force primary halide to ionize, usually with rearrangement to give a more stable carbocation, right? We have mentioned that. So you have carbocation, then you have SN1 and E1, both, since we are creating carbocation intermediate, then with and without rearrangement. Let's solve this problem, predict the products and the mechanisms for the following reactions. When more than one product or mechanism is possible, explain which are most likely. So you have one bromohexane with sodium isoxide. So you have a primary alkyl halide and you have a strong nucleophile. Then you are expecting a measure to be SN2 with minor E2. Here you have only one possibility for the elimination of a HBr. So to give X1N. 2-chlorohexane, it's secondary alkyl halide with again sodium methoxide, strong nucleophile. So you are expecting secondary alkyl halide to undergo measure SN2 with the elimination as a minor. You have two possibilities, H in here and H in here. The elimination of this hydrogen will form more substituted alkene, so this one will be a major. Okay, since this one is disubstituted alkane and could be cis or trans mixture, and of course the other product will be X1N, that's monosubstituted alkane, E2 mechanism. Two-chloro, 2-methylbutane with sodium ethoxide. You have a tertiary alkyl halide. Tertiary alkyl halide is hindered and cannot undergo SN2 reaction. So it will be E2, either this hydrogen and the same, and this one, they are the same methyl group on the same carbon, and this hydrogen. This one, elimination of this, will give more substituted alkene, and this alkene 2-methylbutene trisubstituted alkene, and will be a major E2 reaction. This double bond carrying 2-methyl, 3-methyl, that's trisubstituted. If you eliminate this hydrogen, you get to this compound. It's 2-methylbutane disubstituted, will be minor. Reaction of 2-chloro, 2-methylbutane heated in methanol. So this is tertiary alkyl halide, weak nucleophile, a dielectric, high dielectric solvent, so it will be SN1. Usually with SN1 you find out that there is an E1 product too, and in this case again the elimination of this hydrogen will lead to the more substituted alkane, so this will be the major E1 mechanism. Organometallic compounds derived from alkyl halide and aryl halide, Grignard reagent and organolithium reagent, like methyl magnesium bromide, cyclohexyl magnesium bromide, phenyl magnesium bromide. Reacting alkyl halide with magnesium in anhydrous ethers provide RMGX, via single electron transfer. So Rx will get one electron from magnesium. Magnesium has two outer shell electrons, so we'll provide one electron for halide to form Rx radical anion, and magnesium will be magnesium radical cation. Rx radical will dissociate to give a real alkyl radical and X minus anion, halide ion. R radical, one electron and one electron in magnesium cation radical will form electron, and electron will form sigma bond, so it will be RMG cation. Then RMG cation will find the X to form X minus to form RMGX. Okay? Looking for the Grignard will be RMGX. R will be more carbon, more electronegative than magnesium, so this bond will be polar covalent, where the R or carbon has partially negative and magnesium has a partially positive. We start with Rx alkyl halide, where the X carrying partially negative and R is partially positive. So if we react the RMGX with R prime X, what we expect to find? We are expecting to find R prime. Coupling partially positive, partially negative will couple. That's not the case, okay? And we need copper catalyst to do this reaction, okay? But what will happen actually in this case, okay, that you get exchange. The R prime will take MgX and R will take X, so we have R prime MgX and Rx. For example, reactant of cinnamyl bromide, this is a cinnamyl group. This is called cinnamyl group, cinnamyl bromide with ethyl magnesium bromide and ether, that provide cinnamyl magnesium bromide and maybe other products, but the major product is just exchange. The MgBr will go to the cinnamyl group. Why we are using ether as a solvent for this reaction? Anhydrous. RMGX coordinate or solvated by the ether oxygen. People can just draw it in. Two electrons will go to magnesium. Magnesium will carry negative charge and oxygen will have a positive charge. The other oxygen molecule will donate the two electrons and kick the first bond out, okay, and forming a bond. O will carry a positive charge and magnesium has a negative charge. That's a way to explain the solvation in ether. Alkyl halide with lithium, in this case hexane, because organolithium dissolves in hydrocarbons to form R-lithium and lithium halide. Organolithium reagents are soluble in hydrocarbons. Ether solvent aren't required for this reaction. Give an equation showing the preparation of each of the following organic compound. Isopropyl magnesium bromide. So I start with isopropyl bromide with magnesium and anhydrous ether, we get the compound. How we get phenyllithium? That's the phenyllithium. So we start with bromobenzene, 2 lithium in hexane, we get the compound. How we can prepare cyclohex 1-ene 1L magnesium bromide? Start with the bromocyclohexene, magnesium anhydrous ether, we get the magnesium between the carbon and brom, cyclohexyl 1-ene 1L magnesium bromide. Grignard organolithium reagent reacts as if they are carbanion. This actually, we call it polar covalent bond, but when reactor resembles very like we are at R minus. So Grignard and organolithium reagent are not true carbanion because they have covalent carbon metal bond. However, we can predict their reactivity by treating them conceptually as a carbanion. So RMG, if I have R minus Mg plus, this will go to the hydrogen, react with water to abstract the hydrogen, this cleave out, forming RH, and then OH minus with magnesium is X, ions in the medium. 2-bromobutane with magnesium in ether, where they provide the secondary butyl magnesium bromide, which upon reacting with deuterated water again will be deuterium, oxygen, deuterium. This negatively charged carbon, partially negative, okay, we're reacting here to kick this out to form butane 2D, will be labeled deuterium in carbon number 2. Organocuprate reagent reacting organolithium with copper 1 iodide provide Gilman reagent. It's cuprate, it's lithium dialkyl cuprate, Grignard Gilman reagent. The good about Gilman reagent, it's react with alkyl halide to form what we call it coupling reaction, forming R prime, and of course alkyl copper and lithium halide. For example, if we have 1, 2, 3, 4, 5 bentyl iodide with lithium dimethyl cuprate gives hexane, and increasing the length of the hydrocarbon. Call it coupling reaction of Gilman reagent, and Gilman reagent is organolithium cuprate, lithium dialkyl cuprate. Show how you would synthesize octane from alkyl halide containing no more than 6 carbon. There is a lot of options, okay, but I started thinking about 1-bromobutane. It's 4 carbon atom. I need to synthesize octane with 8 carbons, so it's just twice that how we can couple C4 and C4 together. So I started with 1-bromobutane, lithium in hexane to give butyl lithium in copper iodide and tetrahydrofuran as a solvent, it will give lithium dibutyl cuprate. It's 4 carbon, again plus 4 carbon, 1 bromobutane once again is added to couple here to form octane. See you in the coming lecture.